I'm going to talk today about a project where we are looking at the emissions from the ports of Los Angeles and Long Beach and their effect on the downwind communities of Long Beach. This study is supported by NASA and the California Energy Commission and includes participation with Aerospace Corporation and the University of California, Irvine. Our focus is the ports of Los Angeles and Long Beach, which are the busiest in the Western Hemisphere. They handle 20 million transport equivalent units, which are basically half containers. So continuously activity at the ports 24/7. And these ports are located upwind of Long Beach. So depending on the winds, emissions from the ports may impact communities or may go offshore. In addition to the port and all the freight it handles, there is extensive industry in the area, refineries, wastewater treatment, and so on. Industry that's typically found around ports where access to shipping and the ocean is important. Prevailing winds are from the northwest, controlled in part by the coastal range that defines the Los Angeles basin. And these winds are bifurcated by the Palos Verdes highlands immediately to the west of the refinery, reconnecting on the east. Our study approach that we're going to discuss today, which is a validation experiment between airborne remote sensing and in situ measurements of methane, is used Mako, a thermal hyperspectral imaging spectrometer, and SISTER, the standard instrumentation suite truck-enabled for response platform, which can measure many trace gases and also meteorology, and includes the capability of targeted sample collection for later lab analysis over 60 gases. Emissions are calculated from these data in the case of the remote sensing by simply integrating the column methane and combining that with the winds. And in the case of the in situ SISTER data by a plume inversion approach. We also collect targeted samples to fingerprint the gas and understanding what is affecting air quality. Winds for the port, as noted, bifurcate around Palos Verdes and recombine in their lee in the area of the refinery. Shifting, this of course is for daytime, to onshore further to the east. This creates quite a complex wind flow pattern. As well, nighttime is characterized by a gentle offshore breeze relaxation flow. SISTER2 is our current generation mobile air quality laboratory, which is a package that is installed in the back of a pickup truck, a four-wheel drive pickup truck, or can be put in the back of a boat or on a trailer, weighs approximately a ton, and is installed with a crane. We can mobilize in an hour or two to collect data. Measures many gases by a combination of cavity ring down spectrometers and fluorescence analyzers, methane, propane, ammonia, and so on. We also measure meteorology, aerosol size distributions, aerosol optical depth profiles with a ceilometer to 25,000 feet. We also do measurements of solar spectra to look at ozone, aerosols, other trace gases, and they're based on the solar spectra, as well as radiation from a Geiger counter. The measurements are displayed in real time to both monitor instrument health, but also to guide the sampling. So we have real-time visualization in the Google Earth environment which allows us to circle around and then do targeted sample collections. We're looking at today in this talk 2 surveys, one in June and one in July. The June survey was contemporaneous with Mako, in which we collected data downwind of the refinery through the plume, and we overlapped with Mako within 3 minutes on that particular transect. Several other transects were collected. This was then followed up a month later by a survey without Mako in which air samples were collected. Mako data clearly showed there was wind veering. Here we're showing ACE, which is a very sensitive approach to detecting trace gas, which, however, is not quantitative. Quantitative approach calculations were used, and based on the winds from nearby air quality stations, only 1.5 kilometers away, Mako suggested emissions of 2.4 gigagrams per year at the time of the transect. Using winds that were measured locally by SISTER, we estimated 2.2 gigagrams per year. So the wind uncertainty from a station only 1 kilometer or so away was almost 10%. Now the wind, we can also see there's some wind veering here with the lower altitude plumes. The refinery slopes from the west higher, around 60 meters, to near sea level in the east. Lower winds were more westerly. Upper winds were more northwesterly. And if there had been no veering, then the plume at this time from the refinery would have headed out over the port and off to shore. Instead, the in situ data and the remote sensing show that there's some wind veering, which we've already mentioned, and the plume tracks more along the coastline. Sample canisters were also collected in and out of the plume in a nearby neighborhood of Wilmington. The inversion of the SISTER data for the best case came to 2.51 gigagrams per year. So this is a better than 15% agreement between the two. The uncertainty in this estimate is 11%, actually around 12, based on Monte Carlo simulations using measured parameters. Now that was for an uninformed 4-plume model. Uninformed meant that the model assumed no knowledge from the remote sensing. The best informed model was a 3-plume model using the locations of the plume from the remote sensing and actually produced a higher emissions. This was because plume emissions or measurements were misassigned to the wrong plume and therefore the wrong distance because the in situ model did not include wind veering. As a matter of fact, this absence of wind veering meant that whereas for all of these assumptions, agreement was within 20% between the in situ and the remote sensing measurement for a wide range of assumptions. At the plume level, at the sub-facility level, the agreement was horrible. In fact, it reversed which was the dominant plume. So this highlights how the wind veering was a really critical, important feature at the subplume level, or wind structure at the 100-meter scale was dominating in terms of emissions. At the kilometer scale, we do quite well. We also did a comparison of our canister collected methane with the analyzer. And agreement on most of the cans was very good, with the exception of the Navy Pier, which is jutted out and is presumably clean air, which we'll see in the canisters. But one of those canisters actually seemed to show a hydrocarbon. So the pier was originally, many years ago, an oil pier. And we suspect that there is either abandoned oil well leakage or natural seepage that could have contaminated that one sample. Um, so the canisters allow us to look at the chemical fingerprint of the gas in great detail. Here we're looking at the alkanes. Methane is parts per billion. Ethane through undecane are in parts per trillion. Undecane C8 to C11 are the diesel fraction. And blue, Navy Pier, is cleanest air in this sample, and nothing bigger than heptane. Redondo Beach actually had quite a contribution from the diesel fraction, 8, 9, 10, and 11, which we're measuring in this analysis, which was strange because it was collected on the bluffs with no visible boats. Most likely, later research showed Redondo Beach is riddled with abandoned oil wells under communities, neighborhoods. None of them are visible. They're under grass and pavement. Most likely, we're looking at emissions from some of these abandoned wells, contributing to the pollution level at Redondo Beach. Redondo Beach air flows to Wilmington and the refinery. Wilmington yellow actually shows higher levels of the or similar levels of the lower alkanes and slightly higher levels of some of the mid-range alkanes, the heptane and hexane. These gases would be diluted due to purely the growth of the boundary layer from the beach to Wilmington. DMS revealed it was about double. So the fact that the concentrations are similar or higher represents the addition of urban community in between the two. The refinery is greatly enhanced over Wilmington with both a strong diesel component and a nearly flat C2 through C5. Comparison with oil wells, looking on the right, brown and red, show quite a bit of similarity in the higher levels, the higher components, the diesel components. Less so, the oil wells actually were higher concentrations with some variability of ethane through pentane. Looking into greater detail, we can look again at these gases. Now, Navy Way was very clean and shows a saturation indicated by the pink. Saturation is the amount of enes and ines, in this case butenes, to the butane. So the pinker, the more saturated components. And so there's clearly some source of butene that's coming from a marine source to the Navy Way. Redondo Beach, I should also note that we don't have measurements of alkenes and alkynes greater than C5, so that's why they don't show any details. Redondo Beach shows a fair amount of saturation. Again, we're kind of expecting this might be coming from abandoned oil wells in the area. Less saturated, though, than Wilmington. On the other hand, it does bear some resemblance to 4218 in terms of its saturation level, the oil well in the lower right. These all are very different from the 66 plume, which is very unsaturated. It's cracked, it's refined, it's what they're producing. Green shows some of the aromatics, cyclohexane, benzene, toluene, ethylbenzene, and xylene. And Redondo Beach shows a growing increase from cyclo, which is 5, to xylene, which is 8 carbons. That is somewhat similar to Wilmington, but actually fairly different from the refinery plume. And also kind of a little bit reminiscent of the oil wells. Now, one of the sources, and this is probably explaining what we're seeing at Wilmington, is the gas station. We collected a sample of gas, Arco gas, a cheap gas that has a lot of saturation in the alkanes. Saturated alkanes do not burn as well or as much energy as unsaturated. And so this allows you to, the Chevron gas station, more expensive, has far less. So presumably a big contribution to the Wilmington pollution load is from cheap gas stations. Looking at the difference between the refinery in Wilmington versus the refinery and the oil well, you can see that the refinery is enhancing the diesel fraction over what's in the oil well, which is what the refining is doing. So this concludes my main part of the talk. To summarize, we had excellent agreement between Mako and SIS, even with a wide range of assumptions at the plume, at the overall facility level, not at the sub-facility because of the importance of wind veering. We also noted that there was significant elevation of alkanes and CB-techs in the refinery plume. We showed how we can use this for fingerprinting sources and looking. I'd like to very briefly summarize some of my current projects. One is looking at emissions from abandoned oil wells for NASA. Another is looking at emissions from oil fields and the chemical fingerprinting of them in California. That's for the California Energy Commission. They have an NSF project to look at volcanic emissions from Death Valley. Our focus in the abandoned oil wells is the San Joaquin Valley, which has a plethora, as you can see, gray, of abandoned oil wells to study and look at their emissions. During a recent effort to look at the emissions from an abandoned oil field, it just looks like grass at this point, south of Elk Hills, we went through the Seneca Lease to the east of Midway Sunset along the 166, where drilling was going on. And here we saw a really massive plume of methane and other trace gases. And we saw concentrations up into as high as 30 ppm. And we were able to see a very clear isotopic signature from this plume, which is very neat that we can actually measure isotopes of methane as we go along, indicating it's strongly thermogenic, not exactly what you would expect from a plume. And what was also interesting about the plume, if you look at the methane, is that it's not just where the drilling rig was that there are emissions. They're coming from the whole lease. In other words, many of the wells and infrastructure during this activity are emitting methane at far higher than normal rates. You can also see we mapped out a plume of ethane in the lower right. Not shown, we also mapped out carbon dioxide. At this point, I'd like to just repeat that we are always looking for collaborations with SISTER2 and our analysis capabilities to help out in exciting science projects. Thank you for your attention.